Welcome to Pale Blue Pod, the astronomy podcast for people who are overwhelmed by the universe but want to be its friend.
Aww. I'm Corinne Caputo. I am a comedian, writer, half of the Pale Blue Pod hosting team, and a friend to the universe.
Hell yeah, you are. And I am Dr. Moiya McTier, astrophysicist, folklorist. So happy to be one of the halves of this hosting team. And yeah, the universe and I, we have friendship bracelets.
Oh, yeah. Top 8 on MySpace for sure.
It took a real long time to make the universe a friendship bracelet, Corinne. Like that's
sure
a big
that was
wrist.
Huge. Oh my God.
But Corinne, where are we recording today?
Okay, today we are in a ski lodge at the top of a mountain, and it's cozy. It's like a log cabin. There's fire burning. There's snow crunching outside. I'm not a skier, so this is really just a chance to get like French fries and hot chocolate.
I'm also not a skier. We came here together to this ski
We're
lodge,
here for
not
the
to ski.
We're here for the vibes only, and it's some of the comfiest couches you can get.
Love a comfy couch. I bet everything smells of leather and
It's leather.
wood.
It's wood. It's pine.
Hell
it's
yeah.
snow.
Corinne, do you think snow has a scent?
I think that there is a scent in the air when it snows.
Yeah, I agree. I think snow has a scent. And I'm not just saying that because in so many of my fantasy novels, the romantic male lead smells like snow.
Yes.
I really do. I agree.
You can kind of tell it's going to snow based on the scent sometimes. And then once it's here, it's like quiet, cold, smells different. It's
cold.
distinct. There's a presence to snow.
For sure. So excited to smell that when I step out of the ski lodge. Not to go ski, but just to go home because I got here, I haven't left, and then I'll go home.
Yeah, how do we get down?
I don't know. There are lifts or something, right?
I think so.
Oh, God, I hope so. Well, we're here now, so let's talk about some Aurora.
Yay! It's good we're this far north.
Yes, yeah. That's why we came here, not to ski, but to see the Aurora from the windows.
Safely from the windows inside my warm house.
Yes. The ski lodge has very nice windows. It actually has a balcony. We can go out and see the Aurora over the pine trees with their smelly snow. But that's what we're talking about today.
I'm so excited.
Have you ever seen an Aurora?
I've never seen it. It's definitely like, I feel like it's on everyone's bucket list to like see it, but it's definitely this magical thing in my head about you gotta see it. But every time I look it up online, it's like, do not plan a trip around this. Like,
really?
If you want to go to Iceland, go, but do not expect to see this because you might not see it.
Yeah, because it's not there all the time.
Yeah, and I certainly thought it was as a kid.
Me too. It seemed like almost like a magical portal. You know,
Yes.
like in the what's it called? Philip Pullman's the Golden Compass?
Yeah.
Yeah, like how Aurora there are kind of like the dust and the transporting to other worlds. Like that's
I'm pretty sure.
cool.
Did you ever see Balto? It's this like animated movie. It's not Disney. It's like, some off-brand animated thing. But I loved it as a kid. And he's this dog who has to go get meds for his, like, the young girl who takes care of him. And they live in, like, this isolated community. So he has to, like, run to the next town and get meds. But they're really far north in the snow. And I'm pretty sure there's some kind of scene with the Aurora.
I hope the Aurora guide him to where the medicine is.
I'm trying to remember if he got the meds. He must have. It was a child's
He must have. Yeah, they always work out in the children's movies. As long as you're not, like the mother of the main
as long as you're not the
character,
mom,
you'll be fine.
You're fine. You'll live forever.
I've also never seen an Aurora, but I would love to. It's basic, but it's definitely on my bucket list.
Yeah.
And maybe by the end of this episode, we'll know a bit more about them.
I'll know what I'm looking for.
Yeah, we'll be able to plan our trips better, and you listeners will also be able to plan your trips maybe a little bit better. In general, just like a 101 on Aurora, and then we'll dig into each of these parts deeper over the episode. Aurora are caused when charged particles from the sun interact with Earth's magnetic field and also the particles in our atmosphere.
Okay.
So there are 3 steps there. Particles coming from the sun. That's step number 1. Step number 2 is interacting with our magnetic field. And then step number 3 is those particles interacting with our atmosphere.
Ooh, okay.
So let's start first by saying what the sun is doing. Like, what are these charged particles? Where are they coming from? So the sun is actually constantly giving off what we call in the astro community a solar wind. The solar wind is a stream of electrically charged particles. So if you remember back to your chemistry class, these ions that have either too many electrons or too few electrons, they are coming from the sun's corona. And I think we talked about this in the eclipse episode, but the corona is the atmosphere around the sun. So it's not the sun's surface, but it is the atmosphere of gas and plasma surrounding the sun. And for some reason that we don't totally understand, the atmosphere of the sun is like 1,000 times hotter than the surface of the sun.
Whoa.
The surface of the sun is like 6,000 degrees Fahrenheit, and the corona is like millions.
Whoa.
Like a couple million degrees.
What?
Fahrenheit.
What?
I know, it's weird. It's wacky. But because the corona is so hot, the particles in the sun's atmosphere, in the corona, they move really quickly because temperature and energy and speed, they're related. The reason water or like other things evaporate is because if you add heat to a pot of water, you're also adding energy, and those particles will start moving faster, and eventually they'll move so fast that they like uncouple from each other, and the water evaporates. So that's what's happening to particles in the corona, and the particles get so hot and they move so fast that they can actually escape the sun's gravity, just like the hydrogen and the helium escaping Earth's atmosphere. We talked about this a little bit in the space junk episode. It's called atmospheric loss, and a similar thing happens to the sun. Those particles from the corona of the sun, they travel along the magnetic field lines of the sun. And these lines, they're messy. They change shape, they move, they snap apart, and then they recombine in different places. And we are still actively trying to like pin down the mechanisms that operate the sun's magnetic field. But those charged particles will travel along the sun's magnetic field, and then they'll get shot out through these things called coronal holes.
A t-shirt cannon.
Yes! The coronal hole is just the t-shirt cannon of the sun.
The original t-shirt cannon.
But these holes, they're like leftover sunspots. And sunspots are these dark spots on the sun caused by magnetic activity, really, really strong magnetic activity in that area of the sun, decreases the temperature in that area. I'm not totally sure why. I'm also not totally sure that if I did know why, the explanation would fit into this podcast. But strong magnetic activity causes sunspots, which are these dark, dim spots on the surface of the sun. And those sunspots can become coronal holes, where the stream of particles shoots out. The solar wind was theorized in 1957 by a man named Eugene Parker at the University of Chicago, where fun goes to die.
Get him.
Get him. That's just what I've always heard about University of Chicago, especially at the grad student level. But people were really skeptical about the idea of the solar wind, Corinne. Does the idea of like particles being shot off by the sun sound weird or impossible to you?
I think it feels like how I certainly imagine the sun, and there's this like fluid thing happening around it of like the similar to smoke. Like we were talking about this fluid of smoke.
Corinne, you use fluid.
But I definitely picture like certainly when I would draw the sun, like my favorite drawings of the sun were like a little more, like Van Gogh with the like swirls and things around. And that makes sense. I think solar wind implies to me like a windy winter day, and there's like gusts of stuff, and I know it's not that, but it feels more like, when wind comes across snow and like that top layer of snow goes in the air.
Yeah. I mean, wind is a weird word.
Yeah.
It can mean different things in different contexts. On Earth, the wind that we experience in our everyday life is air being pushed around, most likely due to differences in temperature and pressure in different pockets of air moving towards and with each other. But the solar wind is just this like charged particle stream coming off. And people didn't think it was possible. They were like, no, the sun is just there. We would have noticed if there were particles coming off of it. We would have detected them because we're humans in the 1950s and we know everything. Yeah. Like they really thought they knew so much.
They really did.
I know. But it was confirmed just 5 years later in 1962 when the Mariner 2 spacecraft detected particles coming off of the sun as it was traveling to Venus. The Mariner 2 spacecraft was going to Venus to study it and its atmosphere and stuff.
Yeah.
We really have learned so much in the last 50 years.
We really did.
Me. So then everyone had to be like, oh, okay, Eugene, your solar wind is real. Sure.
Sorry.
And the solar wind is valuable. We should all be very grateful for the solar wind because it protects planets in our solar system from dangerous high-energy cosmic rays or cosmic particles coming from other parts of the galaxy. But it does have a downside. The solar wind can also strip away planet atmospheres.
Oh.
We're pretty sure that the solar wind stripped away most of Mars's atmosphere, that it had a bigger one in the past. It is partially responsible for the atmospheric loss that Earth experiences every year, but we are protected from the worst effects of the solar wind by our own magnetic field.
Okay.
So our magnetic field kind of repels some of the solar wind and the charged particles in it. Mars is not so lucky. It doesn't have a strong magnetic field like we do, so it couldn't keep all of its atmosphere. Very sad. Poor Mars. Aww. I'm crying right now for Mars. And then sometimes the sun gets more magnetically active. It's on this 11-year magnetic activity cycle. So the sun gets more and less active over time. And aurora are brighter. The solar wind is stronger when it's at the peak of that cycle. And when it's at the peak of that cycle, there are things called coronal mass ejections that become more likely. Have you ever heard of a coronal mass ejection? Yeah. A solar flare.
Yes.
These are flares of magnetic activity that shoot out even more charged particles. So it just gets more intense.
And those can tell me if this is just pure science fiction, but those can mess with satellites and things.
Yes, they can. They can mess with satellites. They can mess with our electric grid here on the surface of Earth.
Boy.
They can really do a number. They can do some damage on a lot of our electronics. So the solar wind, great. Let's be happy for it because it's protecting us from dangerous stuff out in the galaxy. But also, if we didn't have Earth's magnetic field, it would fuck us up a lot.
Yeah, sure.
So that's what the sun is doing. That's where the charged particles are coming from. The charged particles come from the sun towards all of the planets in the solar system because it's happening spherically, right? But some of those charged particles will reach us at Earth, and they'll get trapped by our magnetic field, by our magnetosphere, which is this sphere of magnetic energy surrounding the Earth, and they'll get transported to the poles of our planet. But where does that magnetic field come from for the Earth? I'd say basically speaking, the Earth's magnetic field is produced by the motion of our planet's iron and nickel cores. So at the very center of our planet, we have a solid iron and nickel core, and surrounding that is liquid iron and nickel. And as the liquid sloshes around, the motion creates electrical charges, which then generates a magnetic field. When you have electrical charges moving, that generates a magnetic field. And we have a lot of nickel and iron in our core, so it's a really strong magnetic field.
Yeah.
That does come with some concerns, right? Initially, the entire core was liquid, it was molten, and then the inner core condensed, it solidified. The liquid core around the solid core might also start to solidify and slow down. And the shape and the strength and the motion of our magnetic field depends on the motion of that core, and it's changing all the time. So our magnetic field might get weaker over time. There's also this weird thing where sometimes the poles just shift. So the North Pole becomes the South Pole.
What?
And that happens every 300,000 years.
Wait, but Santa, he can't just move all the time.
oh, Corinne, that's a great point. That brings me to the very important difference between a magnetic pole and a geographic pole.
Okay.
So our Earth rotates. We have an equator, and we rotate on an axis. As the Earth spins, we can see geographic North and South poles. That's just, the opposites of the equator. right? Those are the geographic poles. Santa lives at the geographic North Pole.
Oh, okay. Good.
But
amazing news.
Yeah, there you go. But our magnetic field isn't constrained by the Earth's rotation. It doesn't, the north and south magnetic poles are not the same as the geographic poles. So the magnetic poles are also sometimes called dip poles.
Okay.
So I'll talk about the north dip pole and the south dip pole. But the north dip pole is about 300 miles south of the geographic North Pole, and it moves all the time because our magnetic field is in such flux. And that's probably why we use the geographic North and South poles as reference points, because they are not moving.
Okay.
But the magnetic ones are.
Yep.
So the electrically charged particles coming from the sun and the solar wind, they get caught up by our magnetosphere because they are electrically charged. So they're like attracted to these magnetic field lines. And because the field lines run towards the north and south dip poles, that's where the particles get taken. So you get this concentration of charged particles at the north and south dip poles. And that's where you get aurora, is at like these poles. So the northern aurora is called the aurora borealis. I think most people...
That's the one I know.
Yeah, most people know about the aurora borealis. And it's called borealis because Boreas was the Greek god of the north wind.
Ooh.
Got to add in a little mythology there.
Boreas. What a name.
I know. They all had, all of the wind directions had names. There was Boreas in the north. Zephyr, I think, is the west
Zephyr.
wind, which I had an office mate in grad school named Zephyr for a little bit.
I feel like Zephyr's a name we're going to start hearing little kids be called. Like,
I hope so. It's a great name. Zephyr
cool.
was his middle name. Like, his parents gave him a totally normal name, like
and then
normal first name, like John.
Yeah.
But then gave him Zephyr as a middle name, and he chose to go by Zephyr.
Of course. I would do that too.
Yeah, me too. So that's Aurora Borealis in the north, and then Aurora Australis is in the south, and Australis. No, actually, Australis was just Latin for south. So then when we named Australia, they were just like, oh, the land to the south.
Oh, it's over there.
That's all it means. Like the British were like, oh, that's the land to the south where we send all our convicts. Like that's,
yeah, just the bad. We've really colonized this in the worst ways you could.
They did. They really did. Oh, sad pause. But once the particles have been transported to the poles, to the dip poles, by the magnetic field lines, then they can interact with particles in Earth's atmosphere. So we are now at step number 3 to generating an aurora.
Yeah, you really need this perfect cocktail to get them.
Yes, you do.
Yeah.
I think it makes them even prettier, knowing all of the stuff that has to go into it.
Exactly. That's why the websites are like, you're just going to be disappointed if you...
Yeah. Oops. Okay, so let's talk about what Earth's atmosphere is made of.
Okay.
What are these charged particles actually interacting with? So our atmosphere is mostly nitrogen. It's 72% molecular nitrogen, so 2 nitrogen atoms together, N2. It's 21% molecular oxygen, O2, which is 2 oxygen atoms together. And then the remaining 1% is just like a bunch of other particles.
Sure.
It's the carbon dioxide and the water vapor and the methane and the ozone and like everything else makes up just 1% of our atmosphere.
Wow, that's so crazy.
I know.
That it's only 1%.
I know. I know, and I've known for a while that the atmosphere is 78% nitrogen, but it blew my mind that first time I learned it. Because who would think when you're talking about Earth's atmosphere, when you're talking about the air we breathe, like no one mentions the nitrogen.
I know. It's like relatively useless for at least learning in school. Like it's never been brought up. It's never been told to me like this is how plants live or like this is what. Yeah. Yeah.
It's not photosynthesizing anything. It's just extra, but it's most of the atmosphere. And actually, that when I learned that, I felt encouraged to do more interesting world building work, imagining planets with different types of atmospheres, because they can still be oxygen breathing and just have a drastically like the thing they breathe doesn't have to be the majority of the atmosphere, and I felt very free after I learned this.
I'm
about
sure.
Earth.
The creativity.
The possibilities are endless. So that's what the particles in the Earth are. The particles coming from the sun are mostly protons, like hydrogen nuclei, basically. They took a hydrogen atom, all of the motion and the temperature and the energy in the sun's corona stripped away the one little electron. And then you're just left with a hydrogen nucleus, which is just like a proton and maybe a neutron. But then there are also some helium nuclei. Remember, hydrogen and helium are the two most abundant gases or elements in the universe. And then there are some heavier ions, like you'll see some carbon, some iron ions floating around in the solar wind. When the particles from the sun collide with particles in Earth, that energy from the collision excites the particles, meaning that it sends the electrons around those atoms in the molecules to higher energy levels. So shout out to the light episode.
Yeah, that's really shaping up to be like a prerequisite episode for
Good, because it's one of my favorites. The electron moves to the higher energy level, or maybe several electrons move to higher energy levels, but the particles can't stay there. They aren't staying excited for a long amount of time once the energy of the collision is gone. So they'll then drop back down to their original energy levels, what scientists call their ground state. And you'll remember from the light episode, hopefully, that when an electron drops back down to a lower energy level, a photon, a particle of light, is produced with exactly the same amount of energy that the electron dropped.
Yeah, okay, it was like this perfect balance of one for one.
Exactly, yeah. Energy, matter, it can't be destroyed or created. So the energy lost by the electron gets put out into the universe in the form of a photon. And all of these collisions happening together generate enough photons for us to see what's happening. And then the colors that we see, all those beautiful swirling greens and yellows, occasionally you'll see a red or maybe some purple. Those colors depend on the kind of particle being hit and also the height in the atmosphere where the collision happens. So it depends on the type of particle being hit, because each atomic configuration will produce a photon with a specific wavelength and color, because that photon has exactly the same amount of energy that the electron lost. So for example, if you have a collision with oxygen atoms at around like 200 kilometers above the surface of the Earth, you'll see a green-yellow light.
Ooh.
Because that's the color that's produced when the oxygen electrons drop back to their levels. But if you see collisions with those same oxygen atoms, but 100 kilometers higher, above 300 kilometers from the surface, you'll actually see those collisions produce red light. And that is because the extra atmosphere in the way filters out the bluer and greener colors of light. So you're just seeing the red light that gets left behind. So you can see, if it hits sulfur dioxide, it's a different color. If it hits some of the nitrogen, it's a different color. And it depends on the level you are. But most of the aurora you're going to see are going to be green and yellow, because oxygen is very common in our atmosphere. You're probably not going to see a lot of blues and purples, even though they get produced, because they're hard to see against the backdrop of the dark night sky.
Yeah, sure.
But yeah, you can get all sorts of colors. You can get all sorts of shapes, actually, of aurora, and we are still discovering new aurora shapes and like classifying the types of aurora based on their shape and motion.
That's cool.
I know, right? Hey, it's Moiya, and I'm here to give a quick shout out to some of our amazing patrons who help keep Pale Blue Pod going. Thank you, as always, to our sun-like stars, Sharn Llewellyn and Finn. Y'all are so awesome, just holding it down out there with your impressive gravitational field. Thank you so, so much. And also thank you to our latest pre-main sequence stars, Damiana Vance, Hilary Mazur, Michael Baran, and Francis Carter. I hope you're enjoying that deuterium burning in your cores. Maybe one day you'll get to the hydrogen and helium burning in your cores. I believe in you. And you, too, can support us, hear your name on this podcast, and make it to our patron star chart by supporting us on Patreon. You can find the star chart, Patreon info, and more at our website, palebluepod.com, or you can just go right to the source. Head to patreon.com/palebluepod. When I'm recording this right now, we have 33 patrons. When we get to 50 patrons, I'll be giving out free autographed copies of my book, The Milky Way, an autobiography of our galaxy. So go on, support us at patreon.com/palebluepod. We would really appreciate it, and I think you'd enjoy it too.
This episode is brought to you by BetterHelp. I know I feel like my best when I'm confident and have a good grip on my life, but I also know that feeling can be rare. When you're at your best, you can do great things, and sometimes life just gets you bogged down, and you may feel overwhelmed, or like you're not showing up in the way that you want to. Working with a therapist can help you get closer to the best version of you, because when you feel empowered, you're more prepared to take on everything life throws at you. And therapy is helpful for so many reasons. I can't emphasize enough how much therapy has helped me. I used to describe my days like I'm feeling like I'm holding too many balloons, and if I make any movement in any direction, I might lose them all. And these days, it's so much easier to manage my anxiety, myself, my goals, just everything in my life. Therapy is helpful for learning positive coping skills, learning how to set boundaries, and so much more. And I want to emphasize it's not just for those who've experienced major trauma. Anyone can benefit from it. If you're thinking of giving therapy a try, BetterHelp is a great option. It's convenient, flexible, affordable, and entirely online. Just fill out a brief questionnaire to get matched with a licensed therapist, and you can switch therapists at any time for no additional charge. If you want to live a more empowered life, therapy can get you there. Visit betterhelp.com/palebluepod today and get 10% off your first month. That's BetterHelp, HELP.com/palebluepod.
Listening to podcasts is super fun, but do you ever wish you had a community to do it with? You know, like a group of like-minded people who like similar podcasts to you and maybe other stuff. If that sounds like you, then you're in luck, because I'm here to talk to you about the Multi-Crew, which is Multitude's membership program. If you join the Multi-Crew for as little as $5 a month, you get access to Head, Heart, Gut, which is our friendly debate podcast. Each month we pick a different topic, like what's the best symphonic instrument, or what's the best fruit, or what's the best game. And the hosts of the various Multitude shows get together to have a very friendly but formal structured debate about that topic. When I participate in those, I usually win, so you might enjoy Head, Heart, Gut. If you join the Multi-Crew, you also get access to our Pen Pal program, where we'll match you with other people who have similar interests, and you can talk to this community. You can actually engage one-on-one. It's really nice. And of course, by joining the Multi-Crew and supporting Multitude, you're also supporting a small business. We are a collective, a group of independent podcasts, so listener support really makes a huge difference. So, again, for just $5 a month, you get access to Head, Heart, Gut, our Pen Pal program, and the pride of knowing you're supporting a small business. But just for an extra $5 a month, for $10 total a month, you'll get access to our exclusive behind-the-scenes newsletter, our crew-only Instagram account. You know, Multitude has a Finsta. It's fun. We're fun over here. And also first dibs and any updates on other stuff that the Multitude crew is doing. So join at multicrew.club for just $5 or $10 a month, and you won't be disappointed. Now is the part where we might be able to give you some helpful advice if you're planning an Aurora viewing trip. They do happen year-round. Mm-hmm. It doesn't happen when we're at a certain point in our orbit around the sun. They do happen year-round, but they are obviously easier to see at night without the light of the sun blocking them. And so there is this auroral zone in Scandinavia where they market this. So maybe I shouldn't believe them totally. Maybe it's propaganda. Maybe it's a marketing scheme. Yeah. But they do market this auroral zone in Scandinavia as the place where aurora are most frequently visible.
Okay.
Because they can be seen year-round, but they are not. You need to have enough charged particles from the sun coming to interact with our atmosphere. And that auroral zone is, again, in Scandinavia, between 66 and 69, degrees latitude. I couldn't not.
You can't resist.
Yeah. But go to these northern or southern extremes at a time when they're experiencing a very dark period. Once you get north enough, there are places in northern and southern latitudes that experience months of darkness out of the year. So if you're going during a very extended dark period, that will probably increase your chances of seeing some aurora just because there's more nighttime.
Yeah, that makes sense.
And maybe go to the auroral zone where there supposedly are more frequent aurora happening. But one thing that I really love about aurora is that they make a sound.
What?
I know, you think of it as a light show. You think of it as something that's just visual, but they do make a sound. And we've only recently realized, one, that the sound is real, and two, how it happens.
Okay, that makes... Well, now they feel like a firework. You're like, it is this light show with an accompanying noise.
Yes. It's a natural firework. You're right.
Wow. Wait, what does it sound like? Tell me everything.
I'll tell you everything. I'll tell you everything about the sound. So people have been reporting these sounds for a long time. People living in northern settlements have reported hearing sounds from the Aurora Borealis for hundreds of years.
That would scare the shit out of her. Oh my God.
Oh, yes, absolutely.
I would be like, God is real. He's coming for me. He's sending me a message.
And it's an angry one.
And he's not pleased.
God just sent you K, period.
Yeah. Yes. Hey, ... we need to talk.
Oh, and then the typing bubbles, but it goes away.
And then it goes away.
So for hundreds of years, they've been talking about these noises. And in the 1930s, we see reports in the Shetland newspaper that people heard something that sounded like rustling silk or buzzing, maybe a humming or a whistling sound coming from the air when there was an aurora happening. And a lot of people were very skeptical. They were like, no, it's just people in the North Woods being drunk and making stuff up. They were like, actually, it's probably just the rustling pine leaves from all of these trees making this crackling sound. But there was this one Finnish acoustic scientist named Unto Lane, probably, who really wanted to capture the noises from the aurora and prove that, it's not just people getting drunk in Scandinavia and making stuff up. Like, these noises are real.
They're ghosts.
It's ghosts.
It's the ghosts.
It's aliens. So in 2016, Unto Lane published his study on the sounds of the aurora. And for 15 years... before he published that study, he was monitoring solar activity so that he could be sure to catch the strongest aurora. That's longer than the 11-year cycle. So he was guaranteed to see
to get the 11-year cycle
of solar
in there.
activity. Yeah,
totally.
Because he did it for 15 years. And he monitored the solar activity and monitored the aurora happening in his area. And he published the first ever recorded sound of an aurora. Misha, if we can, please put that here. He found that the crackling noise was coming from an inversion layer in the atmosphere about 70 meters above the ground. This is high above the trees that people thought were producing the sound with their little needles. So an inversion layer is this phenomena that happens in our atmosphere sometimes when, it's supposed to get colder as you move up in altitude. But in an inversion layer, it flips so that the temperature increases for a little bit as you move higher through the atmosphere. And that inversion layer somehow can separate the positive and negative electrical charges in the air.
Wow.
During an aurora, there are a lot more electrical charges in the air. So a lot of these positive and negative charges are getting separated. And then the particles coming from the sun can release that inversion layer trap and force the particles to interact. And when you get negative and positive charges interacting, you get static. So the noise that people have been hearing from these aurora it was just static shocks, little static charges in the air, but they're only produced by the strongest aurora, maybe about 5% of them. But we do now have a recording of the Aurora Borealis making a sound.
Wow, that's so cool. And that's so crazy. It's from 2016.
Why? Because you thought it'd be later?
I think in my head, I'm like, we come across this again and again where I'm like, how are we still figuring stuff out? Especially when, people have been watching this for hundreds of years.
Yeah. And reporting the sounds for hundreds of years.
Yeah.
But they didn't have sensitive enough recording equipment
Yeah.
to capture the sound.
Wow. How great that we finally got it.
I know. And how great that the technology was probably developed for porn or war.
Yeah, exactly. Certainly. That's like football is like pioneering like motion capture, like whatever, so that the Super Bowl can be gorgeous.
I kind of hate how technology gets advanced in our world, but whatever, it's fine. So we do know that aurora on Earth exist. We know how they work, and we know that they make a sound, and we know how that sound works. But we also know that there are aurora on other worlds.
Whoa.
Like, Earth is not the only planet or world that has aurora on it. We have seen aurora on Jupiter, Saturn, and Uranus. We know they have magnetic fields. Or maybe we've just seen them on Jupiter and Saturn. But we know that all of these planets have magnetic fields. And we are interested in studying these aurora and their magnetic fields. So if we can study the way that our aurora react to the minute changes in Earth's magnetic field, then when we observe aurora on other worlds, we'll be able to learn about their magnetic fields.
Okay.
Because,
sure.
because we know how the relationship works here on Earth. And again, this is all that deductive reasoning that astronomers have to do. We can look at an aurora and work backwards to figure out what must be happening in that world's magnetic field.
Sure.
And it'll be easier to do for planets in our solar system because we can see them better. But eventually, the hope is that we'll also be able to do this for exoplanets, planets outside of our solar system. But it's not just planets. Moons. Moons can have aurora.
Whoa.
So Ganymede is one of the moons around Jupiter, and it is the only moon that we have confirmed to have its own magnetic field. So it has aurora that we have detected. The Juno spacecraft flew around the Jupiter system and observed a lot of really cool stuff. So we know Ganymede has aurora because of Ganymede's own magnetic field interacting with Jupiter's magnetic field. And I just think it's so cool.
That's really fun.
That we can find these all over in our solar system and hopefully soon outside of the solar system. But we're at this point in aurora science where just having more data about where the aurora are, when they happen, and what they look like is really helpful to science. And can help us learn a lot. And so there's a citizen science project, and I'm such a big fan of citizen science projects because the more people we can get interacting and involved with the scientific process, the better. The more people who have the experience of being involved with science, the better. I'm a huge fan. And it's citizen of the world. It is not citizen of the U.S. science. Just making that clear. But they have this awesome citizen science project called Aurorasaurus. And it's kind of just a hotline, I guess. It started because this researcher saw a lot of tweets about an aurora happening that she didn't expect to be happening. And so she collected data from these tweets. And then she made Aurorasaurus where people can...
this is so fun. I'm on the website right now and it's like a map, charting out everyone's tweets, reporting it. And you can see a positive sighting, a negative sighting, an unverified tweet, a verified tweet. That's so fun.
Nice? Listeners, if you subscribe to our Patreon, I give you research notes for every episode, and that page is definitely in the research notes. You can just track this scientist's logging with help from people all over the world about where aurora are and what they look like.
That's so fun. So you can plan a trip thanks to this tool.
Yes, follow that. Absolutely. Oh, maybe you could use that to see if the auroral zone is actually where aurora are the most common. You can check how much propaganda the auroral zone is. Yeah. But this citizen science project, Aurorasaurus, has already helped researchers learn that aurora are often visible at more southern latitudes than our models predicted.
Oh, okay, cool.
So we're already learning stuff in the year 2020 to 2022. It's all been one very long year. We're learning stuff today. And we're still finding, I said this a little bit earlier, we are still finding different types of aurora that have different shapes and motion patterns. So there's this one that was discovered just in 2020, I think, called that they called the dunes. That's the name they gave to this shape because it looks like these undulating waves in the sky, kind of like sand dunes being blown around in the desert. And that was discovered in part thanks to citizen scientists reporting their findings. Not Aurorasaurus, but like a different project. And then another new shape that we recently discovered. Actually, I think the dunes were discovered in 2016, and then this new shape is from 2020, and it's not really a shape of an aurora, but more of a mechanism that happens. They have named it the diffuse auroral eraser.
Spooky. Okay.
I know. So they found an old video from like 19 years ago that had a video of an aurora on it. They studied the video and they're like, we've never seen that before. And it's interesting because when the video was taken, the camera captured more of the lights than the human eyes could see. So you can see this effect that I'm about to describe in the video, but in person, they recorded 19 years ago, they couldn't see it.
Oh, wow.
So what the diffuse auroral eraser is like, you see an aurora and there's a little patch of light, like a little blurry patch of light, and then it goes away for like a minute and then it comes back.
Oh.
And so they're like, something is blocking out or like erasing this light, but then bringing it back. And they were unsure how that could work. So that's a new aurora type right there.
Whoa.
Discovered because of a decades old recording.
That's really cool.
Mm-hmm. So I just love to think that this magical, mysterious thing that like so many of our ancestors talked about and incorporated into their myths is still kind of mysterious.
Yeah.
We're still learning a lot about it.
I love that there's still mystery and something that, like, the aurora kind of connects human life from the beginning of people being there. Because it's just up there. It's always been.
Mm-hmm. You know, it's on people's bucket list for a reason.
Yeah.
It's one of the most visually striking parts of our night sky, which I think is already visually striking.
Oh my gosh, so moving.
Yeah, it's just another example of the way that the night sky can really bring us all together.
Yeah.
Across cultures, across time.
Mm-hmm.
I love thinking about the fact that some human 5,000 years ago was looking up at the northern lights or the southern lights, and they were wondering, how does that work?
Yeah.
And here I am 5,000 years later, still kind of wondering, hey, how does that work? Even though I know so much more than they did about it. Mm-hmm. I just like feeling that connection.
Yeah, it's really nice. Like, you would have something to bond over if they came to modern day. They wouldn't just be screaming about the phones we have in our hands.
Yes.
It's like, no, we both don't know what's going on.
Look, we both don't know what that star's doing.
We have a lot in common.
So yeah, that's all I have to say about Aurora.
I love it. I hope we catch some. Should we stay till dark in the ski lodge? I hope we catch some.
Let's do it. Let's stay till dark. Let's go get a refill on our hot chocolate maybe, and then we'll do a lookout.
Yes.
For the Aurora. Oh, a stakeout. An Aurora stakeout.
A stakeout. We're stalking it.
Look, if there's anything I would stalk, it would be
the
Aurora.
Mm-hmm. Well, everybody listening, remember tonight as you look up in the night sky and hope to see something green and dancing that you are space.
Mm-hmm. You're just as much space as that Aurora is.
Uh-huh.
Bye.
Bye.
Pale Blue Pod was created by Moiya McTier and Corinne Caputo with help from the Multitude Productions team. Our theme music is by Evan Johnston and our cover art is by Shay McMullen. Our audio editing is handled by the incomparable Misha Stanton.
Stay in touch with us and the universe by following @PaleBluePod on Twitter and Instagram, or check out our website, palebluepod.com. We're a member of Multitude, an independent podcast collective and production studio. If you like Pale Blue Pod, you will love the other shows that live on our website at multitude.productions.
If you want to support Pale Blue Pod financially, join our community over at patreon.com/palebluepod. For just about $1 per episode, you get a shout out on one of our shows and access to director's commentary for each episode. The very best way, though, to help Pale Blue Pod grow is to share it with your friends. So send this episode, this link, to one person who you think will like it, and we will appreciate you for forever.
Thanks for listening to Pale Blue Pod. You'll hear us again next week.
Bye.